All right, guys, we're checking in here on section 11D for IB Math AAHL, solving 3 by 3 linear systems. And I will give you a heads up, this lesson will be a little longer than the previous couple because there's a couple of other intricacies that we have to be mindful of here. To start off, it's going to start the same way as it did with the 2 by 2 systems in that we're going to take the system of linear equations, we're going to put it into our augmented matrix. And the goal from there is still similar in that we're going to try to get 1 in the row 1, column 1 location and zeros underneath that. And again, we're going to try to get a 0 in the row 3, column 2 location. If we can get to that, then that's going to yield us in what's referred to as row echelon form or reduced row echelon form. And then from there, then we can go ahead and try to solve that system. Now, there's a couple things about it. We still want to identify when we have the unique solutions, meaning one solution, when we have no solutions, and when we have infinitely many. Up at the top here, it says if we can reduce the matrix to 1, and then 0, 1, and then 0, 0, 1, that's going to yield one unique solution. You can see that because you're going to end up being able to say that that x3 or that z value is equal to the number that is on the other side of it, the constant. And then we could plug that in to the equation above it, and then plug both of those equations into the top row there to find out what the other values of the variables are. And again, if we can get into this where we see those ones on that diagonal, that's going to yield one solution or a unique solution. Now, sometimes we're going to end up in situations where we don't have any solutions. That generally speaking, that's going to happen if we end up getting zeros across the bottom and a non-zero value on the other side where the constant belongs. Or if we end up having zeros across the bottom, including the constant on the other side, and we end up with a zeros across the middle row and a non-zero in that row. If we end up with any of these scenarios, we say that this has no solution and the system is inconsistent. If, alternatively, if we end up with one of these scenarios, then we're going to have infinitely many solutions. Now, if we take a look at that, the bottom rows are all zeros, but across the middle row, we can get a solution, all right? We can get a solution from any one of these. Therefore, they're going to have infinitely many, and we're going to express the solutions in terms of the parameters, which we'll generally use as S and T. All right, so let's look at some examples here. We have our first 3 by 3 example here, x plus 3y minus z equals 15, 2x plus y plus z equals 7, and x minus y minus 2z equals 0. First things first, put it into our augmented matrix. And then again, the goal, we want the row 1, column 1 to be 1. It already is. That's a great start. But then we want zeros underneath that. So let's take a look at how we're going to achieve that. Right now, I have a 2 in the row 2, column 1 location. Now, if I take row 2 minus 2 times R1, that's going to be 2 minus 2 times 1. That's going to get me 0 here in the row 2, column 1 location. We'll do it. That'll get us there. Underneath that, all I have to do is take the R3 value, which is 1, and subtract the R1 value, which is 0, and I'm in good shape. Now I have 1, 0, 0. We're almost there, but we also need to get a 0 in the row 3, column 2 location. So let's talk how we're going to get that, okay? In order to get that, we're going to take, that's really annoying, sorry about that. What we're going to do is we're going to take 5 times row 3. Now the row 3 value was negative 4. So if I multiply that by 5, I'm going to have negative 20. Then I'm going to subtract 4 times R2 because that's going to be a positive 20. So negative 20 plus 20 gives me that 0. And that will yield a scenario where I have 0, 0 across the bottom row. And then I have negative 17. Now I really want to have 1 in that location. So the final step for the bottom row is to just take this negative 17 and multiply it by 1/17. And that's going to give me, negative 1/17. That's going to give me a 1 in this bottom location. Now, at the same time, I'm also going to want to get a 1 in the row 2, column 2 location. Right now, it's a -5, so I'm just going to multiply by -1/5 across row 2, and that's going to yield me with a 1, a -3/5, and a 23/5. Now, if you notice, you see those 1s in the diagonal, that's going to tell me that this does in fact have a unique solution. And I'm going to go to the next slide to show you how we're going to identify them. So using row 3, z equals -1. Z is just because that's what they called it up here on the previous slide. It could have been x1, x2, x3. This one happens to be x, y, and z. So again, using row 3, z equals -1. Then I'm going to go to row 2, and it's going to say y minus 3/5 times -1, because that's the z value that we just found. And we end up getting a y value of 4 when I solve this equation here. Then I have y and I have z. Let's go up to row number 1. X plus 3 times 4 minus -1 equals 15. Therefore, x equals 2. And I have the solution. It's a unique solution at x equals 2, y equals 4, and z equals -1. Let's take a look at our next example here. Before I try this one, you might want to pause the video and see if you can get there on your own. Again, keeping in mind that once I get into my augmented matrix, I'm going to want down column number 1, 1, 0, 0, and then I'm going to want a 1 in row 2, column 2, a 0 in row 3, column 2, and a 1 in row 3, column 3. Now, we might end up in a situation where I'm not able to get one of those, and this happens to be one of those unique solutions, one of those different scenarios, but we'll talk about that as we go through. So, augmented matrix, 1, 2, 1, 3, 2, -1, 1, 8, 3, -4, 1, 18. So again, we're in a good situation with row 1 because it already starts with the 1. So let's take a look at row 2 and row 3. So if I take row 2 and I subtract 2 times row 1, that's going to get me a 0 there. And similarly, if I take row 3 and I subtract 3 times row 1, that's going to get me a 0 in the third row, first column. And that's exactly what we see here. Make sure you distribute to all values in the row. Don't make a math mistake in that scenario. Next step is going to be trying to get a 1 in row 2, column 2, and a 0 in row 3, column 2. And I'm in pretty good shape right there because I see I have that 5 and the 10. That's going to be easy to help me get that get the 0 in the row 3, column 2. To get myself to have the 1 in row 2, column 2, I'm just going to multiply by -1/5. And for the 0 in row 3, column 2, I'm going to do R3 minus 2 times R2. That's going to get me a 0, but it also is going to end up yielding a 0 in the row 3, column 3. So using row 3, I have 0 equals 5, and that's not a true statement, obviously. So this ends up meaning that this system is inconsistent, has no solution. All right. So I was following along with the rules, and this ended up having no solution there. All right. Let's take a look at example 6 here. And again, I would suggest you pause it and try to do this one on your own to see if you can get there. All right. Now, as I look at this one, this is the first time where row 1, column 1 is not going to start off with a 1. All right. But we can manipulate this pretty easily here. All right. And I apologize, I didn't put my boxes in here, but all I have to do, okay, I'm going to first multiply row 2 by 2. So I'm going to have 2 times this 1 here, and then I'm going to subtract row 1. That's going to get me 0 here. All right. Then I have a 3. I'm going to do 2 times R3 minus 3 times R1. That's going to give me 6 minus 6, therefore 0. All right. Now, could I have done something differently? Could I have started off by swapping row 1 and row 2? I most definitely could have. I just decided not to for this particular example. After that, I'm going to want to make that 3 in row 2, column 2 a 1. So I'm going to multiply row 2 times 1/3. Then I'm going to want to get a 0 in row 3, column 2. All I have to do is add row 2 and row 3. Now, when I do that, you notice I get zeros across the bottom. Zeros across the bottom doesn't automatically mean that it's no solution. It might, but it doesn't automatically. All it tells me is that I'm going to have a scenario where this is going to either, it's definitely not going to have a unique solution, but I have to look at row 2 to determine what other situation I could have. Now, row 3, it says indicates there are infinitely many solutions. So how are we going to write those solutions? We're going to start off by saying z equals t. Okay, z equals t. So we're writing our solutions in parametric form. So if I say that z equals t, and again, I could have said that y equals t. It's all up to you and how you define your parameters. So if I say z equals t, then across row 2, I have y minus t equals 1/3. Therefore, y equals t minus 1/3. So I have z equals t. I have y equals t minus 1/3. The only thing I have left to do is define what x is. In order to do that, I'm going to work with row number 1. So across row 1, I have 2x minus y, but y is t minus 1/3, plus t equals 5. And now I'm just going to solve for x. And what happens here in this situation, the t's cancel out, and x equals 7/3. So I can write my solution, x equals 7/3, y equals t minus 1/3, and z equals t, where t is a real number. All right, so again, my solutions, there are infinitely many of them, but they're going to take this form here, right? And as long as t is a real number, this solution will work. All right. I think this is our last example here, example 7. We have one more, and we have this 3x3 scenario, but it says in this third row, we have the value a, all right? And it says we're considering this system, and what we're going to be trying to do is we're going to try to figure out, okay, we can solve this, but the solution is going to depend on what that a value is. So first thing, put it into the augmented matrix. We're going to do our manipulations, right? And I'm not going to take the time to go through this again because we've already done it a few times now. We're trying to get it to 1, 0, 0 down column 1. Then we're trying to get 1 in row 2, column 2, 0 in row 3, column 2. And what happens is, again, just like we saw before, we ended up with that 0, 0, 0 across the bottom, and it equals a minus 29. So the question is, what does that a have to do with anything? Well, if a does not equal 29, then we have no solution. Why does that make sense? Because if a doesn't equal 29, then we're going to have 0 is equal to some number, and it can't be true. After that, if a equals 29, then we're going to have infinitely many solutions. So in that case, we're going to write out what those solutions are. And again, we're going to start by saying z equals t. Using row 2, we have y plus t equals 3, or y equals 3 minus t. And then again, going across row 1, we have x equals 5 minus t. So as long as a equals 29, then we have our solutions as x equals 5 minus t, y equals 3 minus t, and z equals t as long as t is a real number. All right, so that's it for this one. A little bit longer, a little bit tougher, but the principles are the same. So go ahead and try these practice problems here on page 267, 1 to 7, odd left column, and let me know if you're having any trouble with it, and we'll get together soon. Take care, guys.